mole fraction of solute in 1.0 molal, small m, okay, 1.0 molal aqueous solution is. Aqueous solution is dash. Okay, they gave 4 options. Okay, I didn't remember the option, but the question is this: mole fraction of solute in 1 molal aqueous solution is. They did not mention the solute. Okay, they have given the aqueous solution, so that means solvent is water here. Okay, so how to answer this question? This question is very simple actually. Right, here it is an aqueous solution, that means solvent that we are using here is water. Solvent is water. Solute is not mentioned, but molality is given. Okay, they have given molality, M-O-L-A-L-I-T-Y. What is the molality? Molality is 1.0 molal. Molality is given. They are asking mole fraction of solute. We represent mole fraction by the symbol chi or x. Okay, solute, that means we should put number 2. So what is the mole fraction of solute? This is what they are asking. Okay, so how to find this value is very simple. You know very well, molality, right? It is given 1 molal solution. What is the meaning for 1 molal solution? 1 molal, right? 1 molal. Molal. What is the meaning for 1 molal solution? 1 molal means 1000 gram of solvent. Here solvent is water, right? 1000 gram of water contains 1 molal means 1 mole, contains 1 mole of solute. Okay, now we have 1 mole of solute in water. That's the meaning. 1 mole of solute in 1000 gram of water. You know very well mole fraction of solute. What is mole fraction of solute? Number of moles of solute divided by total number of moles. So here number of moles of solvent and number of moles of solute, if you add, you will get total. Students, remember, mole fraction of solute is nothing but number of moles of solute divided by total number of moles. Okay, how many moles of solute is there? Yes, we have 1 mole. So put 1 in the numerator divided by, okay, and number of moles of solute, again put 1 here. What is the number of moles of solvent? 1000 gram of water is there. Students, remember, 1000 gram of water contains, okay, just remember this value, 55.5 moles of water. How? Very simple. Divide 1000 by 18, that's all. 18 is the 1000 is the weight given. 18 is the molar mass of water. Mass by molar mass will give you number of moles. So if you divide 1000 by 18, you will get 55.5. Remember this value. 1000 gram of water contain 55.5 moles of water. So number of moles of solvent here is 55.5. Therefore, the value should be 1 by 56.5. Can you tell me what is the rough value of this? 1 by 56.5. Just give me some rough value.
0.01.
0.01. 0.01 roughly. Okay. Yes, you are right. So this is the mole fraction of solute present in the solution. Okay. Take down. It's a very simple question. Yeah, it's coming actually 0.017, right? Yeah, take down. So in this manner, if any questions, right, if they ask, right, you can easily answer. But first of all, you just read the question carefully. Okay, then see the given data, right? What are the data given and what we need to find out. Okay, so you know the concepts, so using the concept you can easily answer this type of questions, right? Yeah, so this is a question appeared in the previous year NEET examination. Okay, now let me go to the next part. So we have discussed concentration terms that we are using in solution. Now what I'm going to do, I'm going to discuss the second important part, that is solubility. Solubility. Okay, this is very, very important one. What is mean by solubility? Yeah. Solubility of a substance, this is the usual definition. Solubility of a substance, right? Solubility of a substance is solubility of any substance, right? Solubility of a substance is the maximum amount of substance. Solubility of a substance is the maximum amount of substance. Here substance, what I refer is actually solute. Okay, solubility of a substance is the maximum amount of substance or solute that can be dissolved in a specified amount of solvent. Here the solvent may be 1 liter, the solvent may be 100 ml or 100 grams, whatever maybe it is. You take some specified amount of solvent. In that solvent, what maximum amount of solute can be dissolved? So solubility of a substance is the maximum amount of substance that can be dissolved in a specified amount of solvent at a specified temperature. This is very important because solubility, right, in most cases solubility is affected by temperature. So whenever you give solubility for any solution, any substance in a solvent, you should mention the temperature. It's very, very important. Okay, so this is the basic definition of solubility. Solubility of a substance is the maximum amount of substance, right? Maximum amount of substance that can be dissolved in a specified amount of solvent at a specified temperature. Okay, we usually represent solubility by the symbol S. Okay, so what are the possible units? If usually solubility is expressed as gram per liter. Okay, gram indicate the mass of the solute. Per liter, this unit indicate the solution, right? Gram per liter, or gram per liter is usual unit for solubility, or you can also give the unit in mole per liter. Okay, if you give the unit in mole per liter, it is called molar solubility. If you give the unit in gram per liter, it is called gram solubility. Right? Yeah. For SI unit, you can also give this as kilogram per liter. For SI unit, kilogram per liter. But people not usually, we won't use this kilogram per liter unit. We are using gram per liter unit. Okay, so this is solubility. Now what we are going to do is, see, when you dissolve a substance in water, right, once you reach the maximum amount, if you add a solute, okay, 1 gram, 1 gram, 1 gram, 1 gram, like that, right, at one particular stage complete dissolution takes place, or the maximum amount will reach. After that, no more substance can be dissolved further. We call that solution as saturated solution. Okay, so once you reach the maximum amount, no further amount of substance can be dissolved. We call that solution as saturated solution. So what is saturated solution? Saturated solution. What is meant by saturated solution? No more substance can be dissolved. Okay, no further amount of substance can be dissolved, right, in a solution. We call that solution as saturated solution. Okay. No more substance, right? No more substance can be, that is, we have reached already the maximum. No more substance can be dissolved in a solution, right? We call that solution as saturated solution. I'll put simply SS, saturated solution, right? We have reached the maximum amount, but for saturated solution you must mention the temperature at a given temperature, right? So at a particular temperature, if you dissolve some solute in water or some solute in solvent, you will get a maximum, you will reach a maximum. After that maximum, you cannot dissolve substance furthermore. We call that solution as saturated solution, but you must mention the temperature. At, say for example, at 100 degrees Celsius, right? Just for understanding purpose I am saying this. Suppose, need not be 100 degree, any temperature, right? Say for example, at T equal to, say, 40 degrees Celsius. At 40 degrees Celsius, right? Say I am dissolving some solute, say solute A, right? I am dissolving a gram of some solute A in, say, 100 ml water. 100 ml water, so that I am getting saturated solution, right? But if I increase the temperature little bit, say I am increasing temperature from 40 to 50. If you increase temperature, what will happen? You can dissolve more amount. Okay, so here instead of A, I'll mention some weight. Say for example, I'm dissolving 10 gram. See, at 40 degrees Celsius, students observe carefully. At 40 degrees Celsius, I am dissolving 10 gram of solid in 100 ml of water, and I am getting saturated solution. Suppose if we increase temperature, you can dissolve even more than that. You can dissolve, say, 12 gram in 100 ml, so that you get saturated solution. So for saturated solution, you must mention the temperature, right? That is why I am saying. So what is saturated solution? It is a solution in which no more substance. Saturated solution is a solution in which no more substance can be dissolved further, right? In a solution, we call that solution at a given temperature. That solution is called saturated solution, right? Now, students, actually what happens in the saturated solution? Say for example, I'll take some water in a vessel. It need not be a water. You can take any solvent actually. I'll take some solvent and I'll put excess amount of solid. Okay, so this is my solvent. I'll put excess, I'll keep on adding substance. At one stage, what will happen? The substance simply deposit. Okay, some amount dissolved. So here we have dissolved solute. And we also have some undissolved substance, because I have added excess undissolved solute. Students, observe this carefully. Let the temperature is T. let the temperature of the solution is T, right? At constant temperature, right, some amount of substance is already dissolved, that is the maximum amount, right? Remaining amount of substance simply settle down and remains as solid. Now in the solution, actually what happens, listen, the solid particles present, right, the substance which is present as solid here, they dissolve and go to the solution. This process is called dissolution. Students, turn on your camera, all of you. Turn on your camera. Right? What is dissolution? Dissolution means solid particles, right, goes into the solution, okay, or get dissolved. Solid get dissolved in solution, or it disappears in solution. Get dissolved in solution, we call that process as dissolution, right? So in the saturated solution, students observe carefully, in what is saturated solution? No more substance can be dissolved further. So once you reach a saturated solution, okay, the remaining amount of substance simply settle down and remains as solid. Now in this saturated solution, right, the solid particles present here, okay, will dissolve. At the same time, the particles present in the solution, okay, they approach the solid surface and get deposited. It is called crystallization. Crystallization. Students observe carefully. Crystallization means the particles in the solution, okay, particles in solution. What particles? Solute particles. The solute particles in solution, right, approach the solid surface and get adhere on solid surface, which is called and become solid. It will approach the solid surface and become solid. So this process, the solid solid goes into solution, is called dissolution, and the particles present in solution become solid, is called crystallization, right? At a particular temperature T, the two process, that is dissolution, see the forward one is dissolution and this one is the crystallization. Okay, I'll put simple letters D, C. Solid becoming solution is D. Solid goes into solution is D. Particle present in solution becomes solid is C, crystallization. Students observe carefully. At a temperature T, the two processes will come to equilibrium. Right? What is equilibrium? Rate of dissolution. Rate of dissolution, I will put simply D. What is D here? Rate of dissolution. And rate of crystallization. Crystallization, these two become equal. Okay, these two become equal. Once this stage is reached, we say that the substance or the system is at dynamic equilibrium. I am not saying simply equilibrium, I am saying dynamic equilibrium. Why? Even the equilibrium is reached, dissolution and crystallization occurs continuously. Students, observe carefully. See, what I told you is the solution is saturated. If the solution is saturated, no more substance can be dissolved further. Therefore, excess substance simply deposit, okay, and remains as solid here. These particles in solid, right, will keep on going to the solution. Right? This is called dissolution. And the particle present in solution will approach the solid surface and become solids. And that process is called crystallization. In saturated solution, these two occurs continuously. Dissolution, crystallization occurs continuously. Right? And at a given temperature, right, you will get an equilibrium. What is equilibrium? Rate of dissolution and rate of crystallization become equal. Right? Rate of dissolution and rate of crystallization become equal. We call that stage as equilibrium stage. and I'm using a term called dynamic equilibrium. Why I am calling this dynamic equilibrium? Because even after the attainment of equilibrium, the dissolution and crystallization takes place continuously. Okay, right? So at dynamic equilibrium, whatever solution, right, that you are having is called a saturated solution. So this solution, once it reaches dynamic equilibrium here, then we call this solution as saturated solution. Okay, so remember students, in saturated solution, okay, dynamic equilibrium exists between dissolution and crystallization. I repeat, in saturated solution, dynamic equilibrium exists between dissolution and crystallization, right? So this is a very important one, keep this in mind. Then since you have dynamic equilibrium, then Le-Chatelier principle will come in picture. Okay, so we'll discuss that, how that concept is used here. Okay, Le-Chatelier principle you might have heard about in your 11th standard. Okay, right now, so I just introduced what is solubility, right? I just introduced what is solubility, right? Then what is meant by saturated solution? In saturated solution, we get what is called a dynamic equilibrium. Okay, whenever a solution attains dynamic equilibrium, you can call the solution as saturated solution, right? Then now what I'm going to do, under solubility, we are going to focus on two solutions. Under solubility, I'm going to focus on two solutions. What is that? Solid in liquid solution, solid in liquid solution, okay, and the other one is gas in liquid solution. Solid in liquid solution, the other one is gas in liquid solution. These two solutions we are going to focus here. Okay, we also have liquid in liquid solution, okay, which is actually very simple, right? If time permit, we'll do that. Now, so first let me take solid in liquid solution, right? Solubility of solid in liquid solution. Okay, so solid here is solute and the liquid here is solvent. Okay, solid in liquid solution means solid is the solute and liquid is the solvent. Now, what are all the factors which affect solubility of solid in liquid? Okay, factors which affects the solubility of solid in liquid. What are the factors which affects solubility of solid in liquid? Okay, I'll just list out. Number one, nature of solute. Nature of solute. Number two, nature of solvent. Number three, temperature. Number four, pressure. Okay, these four factors affects the solubility of a solid in liquid. Okay, first let me focus on these two, nature of solute and nature of solvent, then I'll come to temperature. How nature of solute and nature of solvent affects the solubility of a solid in liquid. Okay, yeah, so this is actually a very simple one. Students, you might have heard about this. there is a rule called, it's a basic rule, like dissolves like. There is a rule called like dissolves like. Okay, what is meant by that? Like dissolves like, what is meant by that? It means polar solvent dissolves, okay, polar solvent dissolves polar substance or polar solute. Okay, I am using the word substance here. Okay, here substance means solute. Polar solvent dissolves polar substance. Similarly, non-polar solvent dissolves non-polar substance. This is what we call as like dissolves like rule. Okay, like dissolves like rule. According to this rule, polar solvent, suppose your solvent is polar, it will dissolve polar substance. If your solvent is non-polar, it will dissolve non-polar substance. Okay, now what is meant by polar substance, what is meant by non-polar substance, right? Okay, listen, what is meant by polar, what is meant by non-polar? Students, observe carefully here. Non-polar means, okay, non-polar substance, we say non-polar solvent or non-polar substance. Okay, let me give some example for non-polar solvent. Okay, we give a molecule, we say a molecule is non-polar based on the dipole moment value. If dipole moment value mu, if it is 0, if dipole moment value is 0, for a molecule, we call those substance or those solvent as non-polar. Okay, the good example, okay, we have lot of examples actually for non-polar solvents. Okay, alkanes, right? Alkanes, cycloalkanes, right? Benzene, carbon tetrachloride, carbon disulfide. These are all, okay, few examples. See, alkanes means all alkanes. Okay, very specifically for solvent we use we use N-hexane. N-hexane is a liquid. We use N-hexane, N-heptane. Right, these are all alkanes. N-hexane, N-heptane, they are all solvents, non-polar solvents. We also have cycloalkanes. For cycloalkanes, we have plenty of example. I'll give a few here. Cyclopentane solvent, cyclohexane solvent, cyclohexane. Right? These are all few examples for non-polar solvent. Then benzene, carbon tetrachloride, carbon disulfide. I have given few examples for non-polar solvents. Okay, note down. This is very important. Now I'll give few examples for polar solvent. Which are all the solvents are called as polar solvent. Polar solvent means the molecules, solvent molecules have some dipole moment. Dipole moment is not equal to 0. They have some dipole moment. What are all the examples for polar solvents? Yes, water is a polar solvent, right? Then alcohols, methanol, ethanol, polar solvent. Then dimethyl formamide, DMF. We simply say DMF, dimethyl formamide. Then DMSO, dimethyl sulfoxide, dimethyl formamide. I'll write here dimethyl formamide, and this is dimethyl sulfoxide. Plenty of examples are there. Dimethyl sulfoxide, sulphoxide, sulfoxide, sulphoxide, sulfoxide. Students, plenty of examples are there. I have given few here. These are all examples for polar solvent. This is non-polar solvent and these are polar solvent. Okay. Similarly, for solute also we have polar solute and non-polar solute. Let me write to the next page. In solute, okay, are the substance. We have polar substance, right? It can be polar substance or it can be non-polar substance. Okay. Usually ionic compounds, students, observe carefully. Ionic compounds, sodium chloride, potassium chloride, right? I am giving some example here. See, sodium chloride, potassium chloride, etc., etc. These are all examples for few ionic compounds. Okay, ionic compounds are usually polar substance, and some compounds they have. See, polar means dipole moment is not zero. Polar moment means the molecules have some dipole moment. Dipole moment is not zero. Okay, the hydrogen chloride, right? And we have plenty of examples. HF, right, or HBr, etc., etc. Plenty of examples are there. These are all examples for polar substances. Non-polar substances, yes. Non-polar means dipole moment should be zero. Non-polar substances. Okay, say for example bromine, Br2 is a non-polar substance, right? Similarly, substance like sulfur, right? S8, sulfur. I'm just giving few examples. Okay, usually homodiatomic molecules, right? Homodiatomic molecules, right, are non-polar substances, right? Yes, we have plenty of examples like that. Okay, say right, let it be. We'll discuss with some examples so that you can easily understand this. So remember, in solvent we have polar solvent. See, in solvent we have polar solvent, non-polar solvent and polar solvent. In substance, solute also we have polar substance, non-polar substance. What like dissolves like rule says, if your solvent is polar, then it can easily dissolve polar substance. Okay, say for example, there's an example. If I take water, okay, this is my solvent, it can dissolve, right, polar substance, say sodium chloride. Okay, it can dissolve HCl. Okay, it can dissolve potassium chloride. Okay, all these substances can be readily dissolved. Can we dissolve naphthalene here, students? Naphthalene. Can I dissolve naphthalene in water? So these are all solutes, possible solutes. Naphthalene is non-polar substance. Naphthalene is non-polar, whereas your solvent is polar. Can naphthalene be dissolved in water in larger extent? Students, turn on your camera. Students, all of you turn on your camera. Yeah. Is naphthalene dissolved in water?
No, sir.
Why?
No, sir.
Yeah, according to like dissolve like rule, naphthalene is non-polar. Your solvent is polar. Therefore, this substance, okay, is almost insoluble in water, right? It is insoluble. So I can say simply it is not soluble. right? Because it is non-polar, right? Like this we have plenty of examples, right? So keep this in mind. Polar solvent can dissolve polar substances. Similarly, if you take non-polar solvent, say for example, I'll take benzene. Benzene is a non-polar solvent, right? This is non-polar. Benzene is non-polar. Therefore, in benzene, listen, I'll give some substance. You try to tell me which one can be dissolved, which cannot be dissolved, right? Number one, I'll take naphthalene. I'll take wax. I'll take sodium chloride. Okay, I'll take some substance like HCl, right? Can listen here, student. Now solvent is non-polar. Naphthalene is a non-polar substance. I'll write here. Naphthalene is non-polar substance. NS. This is non-polar. Sodium chloride is polar. Okay. NP. NP means non-polar. This is polar. Now tell me which one dissolves, which one does not dissolve.
NaCl and HCl dissolve.
Yeah. Naphthalene dissolves because non-polar. This is non-polar. Naphthalene dissolves in benzene. Wax also dissolves in benzene. But sodium chloride and HCl, since they are polar, they are not dissolved in benzene. Is it clear, student? So, depending upon the nature of the solute and nature of the solvent, okay, solubility will vary, right? Actually, see here naphthalene, we say that naphthalene is insoluble in water, but actually it has very small amount of naphthalene can be dissolved. So we can say that negligible amount of naphthalene can be dissolved. Okay, that is why we say simply it is insoluble. Insoluble means don't think that even one molecule cannot go into a solution. No, it's not like that. Naphthalene also dissolve, but the amount dissolved in water is negligible. So we say that okay, naphthalene is insoluble in water. Okay, yeah, students keep this in mind. Now see here I have given the information based on nature of the solute and nature of the solvent. Your solute can be polar or non-polar. Your solvent can be polar or non-polar. Okay, then to decide whether solid dissolves in water or not, okay, then you can use this like dissolves like rule. But for like dissolve like rule, we have few exceptions also. Okay, say for example, if you take sugar molecules, right? I'll take water. So water is my solvent, which is polar. Now I'm going to add sugar. Sugar, on average, it is non-polar. Okay, on average, right? If you take sugar molecules on average, it is non-polar. Now, the question is the sugar soluble in water or not? Students? Is sugar soluble in water or not?
Yes, sir.
Okay, you know very well. Yes, it dissolves. Sugar dissolves, right, in water. Yes, it is soluble. Sugar is soluble in water. Okay, that's a well-known one. But it contradicts the like dissolve like rule, isn't it? Okay, it contradicts like dissolve like rule. Why? Because here dissolution is due to formation of intermolecular hydrogen bonding. Okay, here solubility is due to intermolecular hydrogen bonding. Is due to intermolecular hydrogen bonding. We are going to discuss about this, right, in other chapters, but right now just keep this in mind. Why sugar dissolves in water? Even though it is on average it is non-polar, but it dissolves in water. Why? The reason is it forms intermolecular hydrogen bonding with water. So due to the formation of intermolecular hydrogen bonding, okay, sugar molecules, right, goes into the water and becomes solution. Okay, it dissolves simply. Is this clear, student? Any doubt? So there are exceptions available for like dissolves like rule. Okay, and these are few. Now let me go to the next one. So this is the first factor, that is nature of the solute and nature of the solvent. Okay, like dissolves like rule will tell you about how nature of the solvent and nature of the solute affects the solubility. Okay, then the second one, so this is number one. Number one represents like dissolves like rule. This is indirectly gives you the nature of the solute and nature of the solvent. Okay, how solubility depends on nature of the solute and nature of the solvent. Okay, then the second one is the effect of temperature. How temperature affects the solubility? Students, observe carefully. What we are doing is we are talking about, listen, students, we are discussing about solubility of solid in liquid. Okay, solubility of solid in liquid. This solubility is affected by many factors: nature of solute, nature of solvent, temperature, pressure. We discussed these two now. Okay, under like dissolves like rule, we discussed nature of solute, nature of solvent, how these two affects the solubility. Now the second term that I am going to discuss is temperature. Right? How temperature affects the solubility of a solid in liquid. Okay? Right? Solubility of solid in liquid. How temperature affects solubility of solid in liquid. Okay, this is what we are going to discuss now. Right, listen. Students, this is very important. When you dissolve any substance in water or in solvent, the solid molecule, the solid substance, okay, gets separated and the particles goes into the solution. And after some time, the solid will disappear, correct? If you put a solid in water, the solid particles first get separated and goes into solution and they disappear. This is what we call as dissolution. Okay, in dissolution, okay, this is O. In dissolution of a solid in liquid, okay, heat may be released or heat may be absorbed. When you dissolve any substance in water, okay, I'm taking water as an example, as solvent. Okay, you take water as solvent, you put some substance in water. If the substance dissolves, okay, heat may be absorbed. Heat is absorbed. Suppose if heat is absorbed. If heat is absorbed, we call that dissolution as, or we call that solution as endothermic solution. Okay, where delta H is positive. Delta H positive means endothermic. So dissolution is endothermic. Students, observe carefully. When you put a solid in water, the solid dissolves. During the process, heat may be absorbed. If heat is absorbed in dissolution, we call that dissolution as endothermic dissolution or endothermic solution. If heat is released, sometimes heat may be released during the formation of solution, right? Then delta H will be negative, we call that dissolution or a solution as exothermic solution. Exothermic, endothermic, exothermic. Exothermic means delta H is negative. Endothermic means delta H is positive. Delta H means change in enthalpy. Change in enthalpy of solution. Change in enthalpy of solution is positive if heat is absorbed. Change in enthalpy of solution is negative if heat is released. Listen, students, you might have observed this. Suppose if you dissolve some solid, okay, in water, right, and if you touch the surface of the container, okay, it appears cold. You can feel some chillness. It means heat is absorbed by the substance present in solution. So whenever heat is absorbed, okay, the surface of the vessel appears cold. Okay, we call that solution as endothermic solution. In some substance, suppose you take concentrate sulfuric acid, right? If you add concentrate sulfuric acid in water, right, and if you touch the vessel, surface of the vessel appears hot. Why the vessel appears hot? Because heat is released here. If heat is released, we call that solution as an exothermic solution. Okay, now listen, how temperature affect solubility of a solid in liquid. To understand this, you must know whether the solution enthalpy of solution is positive or negative. Okay, suppose if delta H for solution, right, we write like this normally, delta H for solution. I'll put SOLN, which means solution. If delta H for solution is positive, that means endothermic. If the solution is endothermic, if the dissolution is endothermic, then if you increase temperature, right, as temperature increases, if temperature increases, solubility increases. Students, observe carefully, very, very important. If enthalpy of dissolution is positive, that means heat is absorbed. So for the dissolution of substance, heat required, that is the meaning, heat is required. So if you supply heat, that is if you increase temperature, solubility will increase. Right? Instead, if delta H solution or delta H for dissolution, if it is negative means heat is released. Okay, if heat is released, in this case, if you increase temperature, if temperature increases, solubility decreases. Solubility decreases. Is this clear, student? Students, everyone turn on your camera. Turn on your camera. Yeah. Students, is this clear? Any doubt in this? Is the concept clear?
Yes, sir.
Okay. So, to understand the effect of temperature on the solubility of solid in liquid, okay, the main thing that you should know is the enthalpy of the solution. If it is positive, in this case, if you increase temperature, solubility will increase. You can dissolve more and more substance, okay, as you increase temperature. If enthalpy of dissolution or enthalpy of the solution is negative, okay, that means the dissolution of substance will release heat. In that case, heat is not required. That's the meaning. So if you supply heat, then solubility will decrease in that case. Okay, so keep this point in mind. Very, very, very important. Then the third factor is effect of pressure. Okay, let me come to the next one. Third factor, effect of pressure. How pressure affects the solubility of solid in liquid. Solubility of solid in liquid. Students, observe this carefully. Our solute is solid here. Usually pressure has insignificant effect, right, on the solubility of solid in liquid. Okay, or we can say simply pressure has no effect, right? Pressure has no effect, right, or insignificant effect. That's the right word we should say. Insignificant effect. Pressure has insignificant effect, right, on the solubility, of solid in liquid solutions. So you need not worry about pressure. Okay, for solubility of solid in liquid, students, for solubility of solid in liquid, you should focus on, okay, these two factors, that is nature of solute and solvent. Number two, temperature. These two are the most important quantities. Okay, pressure has insignificant effect in the solubility of solid in liquid solution. You need not worry about that. Is this clear, student? Any doubt?
No, sir.
Okay, so we have discussed solubility of solid in liquid solution. Now I'll go to the next one, that is solubility of gas in liquid. Next one, solubility of gas in liquid. Gas in liquid. Okay, here also nature of solute and nature of solvent. Here gas is solute, okay, and the liquid is solvent. Here also nature affects the solubility. Okay, nature affects the solubility. Since we have discussed already under like dissolves like rule, I need not go into the discussion of those things here. Okay, and I am going to concentrate only the effect of temperature and pressure here, right? Students, here also solubility, right, depends on number one, nature of solute and solvent. Okay, since we have discussed about this in the under like dissolves like rule, so I am not going to discuss here again. Okay, second factor, that is temperature and pressure. These two are very, very important, and very specifically, since gas is involved here, pressure contribution is very, very important. Okay, so we need to focus on effect of pressure on the solubility of gas in liquid. Okay, so let me discuss that one here. What is the effect of pressure on the solubility of gas in liquid? Number one, effect of pressure. Okay, students, listen carefully. Suppose I'll take a container which contains some solution. I have some solution here. Above the solution we have vapors. Okay, this is a solution, right, and above the solution I have some vapors. This solution may contain 2 component, may contain 3 component, 4 component, whatever it is. Okay, and some components are volatile. Okay, the components which are volatile will go to the vapor state. Students, listen carefully. The solution may contain 2 component, 3 component, 4 component, right, any number of component, and the components which are volatile, only volatile component will go to the vapor phase. So this is vapor. Now let us say, for example, I have 2 or 3 components in this, 2 or 3 components in the vapor phase. You take any one component, or you have to define each component separately, right? What is the effect of pressure? Listen, to understand effect of pressure, okay, a scientist called Henry, he gave a law. It's called Henry's law. To understand effect of pressure on the dissolution of gas in liquid, Henry gave a law. What's the law? According to Henry's law, the vapor above should behave like ideal gas. Should behave like ideal gas, which is not necessary right now. You need not worry about that. Okay. Now let us assume that I have 2 or more components here. 2 or more component. Okay. Say component A, component B. Okay. I have some number of A molecules, some number of B molecules in the vapor state. Now what Henry's law says that, and let us assume the temperature is T. At a given temperature, the partial vapor pressure, okay, partial vapor pressure, the vapor above the liquid will exert some pressure on the surface of the liquid. Students, observe carefully. The molecules present in vapor state, okay, the vapor above the liquid will exert some pressure on the surface of the liquid. We call that pressure as vapor pressure. Why I am using partial vapor pressure? See, I have 2 different molecules here in the vapor state, A and B. What is the pressure exerted by A alone? Or what is the pressure exerted by B alone? It is what is called partial vapor pressure. Partial vapor pressure of a component, partial vapor pressure of a component above a solution, partial vapor pressure of a component above a solution is directly proportional to the mole fraction. Okay, I'll repeat. Partial vapor pressure of a component above a solution is directly proportional to the mole fraction of that component, mole fraction of the component present in solution, present in liquid phase. Liquid phase at a given temperature, T. Students, observe this carefully. Partial vapor pressure of a component, okay, say for example, I'll take the component A. Partial vapor pressure of component A present above the liquid, okay, above a solution, is directly proportional to mole fraction of the component. See, in the solution or in the liquid phase also I have molecules A and B, right? And you find out what is the mole fraction of A in the liquid phase. This partial vapor pressure of A is directly proportional to mole fraction of A present in the solution. This is what we call as the Henry's law. Okay, students, is this clear? According to Henry's law, partial vapor pressure of a component, the component may be A or maybe B or maybe C, whatever it is, partial vapor pressure of a component above a solution, okay, is directly proportional to the mole fraction of that component present in the liquid phase at a given temperature T. Okay, so in general we write like this, we write simply like this: partial vapor pressure of a component is directly proportional to mole fraction of that component present in the solution. Okay, right? Let me write in general ith component, partial vapor pressure of some ith component is directly proportional to mole fraction of ith component present in the solution. Okay, RPI equal to, whenever you convert proportionality into equal, we should introduce a constant. So let me introduce a constant capital K, and I'll put a H in the subscript. It is called Henry's constant or Henry law constant. This is multiplication symbol. Okay, Pi equal to KH into Xi. What is Pi? Pi is partial pressure of ith component present above the solution, which is equal to Henry's law constant into mole fraction of that component in the solution. Okay, this is called Henry's law constant or Henry's constant. Henry's law constant. Henry's law constant. Okay, take two. Is this clear, student? Any doubt? Students, are you able to follow this?
Yes, sir.
Yeah. Solubility of gas in liquid. Okay. Solubility of gas in liquid. The solubility is mainly affected by pressure. So if you want to understand the effect of pressure, right, on the solubility of gas in liquid, we have a law called Henry's law, right? What this Henry's law says, according to this law, partial vapor pressure, right, of a component, right, above a solution is directly proportional to the mole fraction of the component present in the liquid phase. Okay, so partial pressure is directly proportional to mole fraction, where KH is called Henry's law constant. Right? Suppose, see this equation, it is a very simple equation. This equation is an equation, okay, it looks like an equation of the straight line. Y is equal to mx. So you know well, this is the general form of a straight line equation, y equal to mx plus c. But here, if you plot pi in y-axis, xi in x-axis, okay, there is no c here, so in this case you just remove the c. So this equation is similar to the equation of the straight line y equal to mx. This equation is similar to the equation of the straight line y equal to mx, and intercept is 0. Intercept is 0. So what is meant by that? Suppose if I plot, okay, let me do it in the next page. Yeah, suppose, students observe this carefully. Suppose if I plot, see what we are having, partial pressure is equal to Henry's law constant and xi, x, okay, xi or x. Suppose if you have only one component above the liquid surface, only one component, suppose A alone is present, then you need not put I and all. You can write simply like this. If you have two or more component above the liquid surface, then only you should mention which component you are talking about. Okay, whether it is A or for B or for C, right? You have to mention that. Suppose if you have only one component above the liquid, for only one component, for only one component above the liquid, okay, then you need not put A, B symbol and all. You can write simply P is equal to KH into mole fraction. Now in this case, listen, if I plot this pressure, vapor pressure in y-axis, and if I plot this mole fraction in x-axis, I will get a straight line with a positive slope, because here it is positive, and that slope and that straight line passes through the origin because no intercept. Okay, so if I plot partial pressure in y-axis and mole fraction in x-axis, okay, listen, as the pressure increases, if you increase pressure, mole fraction will increase. Mole fraction increases means solubility increases. Okay, that's the meaning. So you will get a straight line passing through the origin. You will get a straight line passing through the origin. Okay, I should not show in the negative side actually. It will go like this, right? And what is the slope of this straight line? Slope is equal to, okay, you know very well, this is y equal to, it is something similar to y equal to mx. So this m is nothing but slope, right? Slope here is Henry's law constant kh. So if you want to find Henry's law constant for a particular component, what you have to do, increase the pressure of the component, okay, above the liquid surface, okay, and find the mole fraction in the liquid, right? If you know the partial pressure and the mole fraction, you just plot a graph and find the you will get a straight line. Find the slope of the straight line. That slope is equal to Henry's law constant. That slope is equal to Henry's law constant. Students, is this clear? Any doubt here?
No, sir.
Okay, take two. And listen, students, this is very important. Henry's law constant kh is a constant for a particular component, or a molecule. What is meant by that? For nitrogen, we will have, suppose if you have nitrogen gas above the liquid, for nitrogen gas we will have a value of Henry's law constant. For oxygen gas, you will have a different value of constant. Okay, so the Henry's law constant will differ from gas to gas. Okay, say for example, I'll give you values of Henry's law constant at a temperature of 293 Kelvin. I'll give some few examples. See, at 293 Kelvin, students, observe carefully. I'm going to give only two gases. Plenty of examples are available in your book. Okay, for helium and hydrogen, Henry's law constants are given at the same temperature, 293 Kelvin. For helium, the value is 144.97 kilobar. Okay, the value is given in kilobar. For hydrogen, the value is 69.16 kilobar. Students, observe the values carefully. Okay, for helium it is 144, for hydrogen it is 69.16. Okay, what does this indicate? At the same temperature, two different gases have different value of Henry's law constant. What does this indicate? It indicates that, okay, let me take the show the equation again. See, this is Henry's law equation. Okay, if I rearrange this equation, kh equal to, I'll get P by X, correct? kh equal to P by X. When you'll get higher value of kh? When kh will increase, students? X, actually X is the mole fraction. Mole fraction represents solubility. Students, observe carefully. Mole fraction is the solubility actually. If mole fraction in the liquid increases, which means solubility increases. So, if X is high, what will happen if X is high?
KH will decrease.
KH will decrease. Appo, lesser value of K, helium, hydrogen, C, lesser the value of KH, higher is the solubility, am I right?
Yes, sir.
Okay, yeah. So here mole fraction is high. Here mole fraction is low. Mole fraction of H2 is high. Here mole fraction of helium is low, which means solubility of helium, okay, in here I didn't mention the solvent. Actually here solvent is water. Okay, here solvent is water. I didn't mention the solvent here. Here solvent is water. So in water, okay, if you see the dissolution of helium and dissolution of hydrogen, which is more soluble? Hydrogen is more soluble because KH value is low. So keep this point in mind. Lesser the value of KH, higher is the solubility of the component in in a particular solvent. Okay, yeah, let me write in the next page. So what I'm saying, lower the value of KH, okay, higher is the solubility, higher is the solubility of gas, solubility of gas in liquid, very important, no doubt. If Henry's law constant is high, that component dissolve in lesser extent. If Henry's law constant is low, that component dissolve in larger extent. Okay, now let me ask a question based on this. Okay, say at 298 Kelvin, students observe this carefully, at 298 Kelvin, right, I'll take two gases, argon gas and carbon dioxide gas, right. For argon gas, KH value is given, right. Here again solvent is water. Okay, let me mention here, solvent is water. Argon gas has KH value 40.3 kilobar. Kilobar is the unit of pressure. Okay, bar is the unit of pressure. Kilo, it is given in kilobar, and it is just 1.67 kilobar. Students, what does this indicate?
CO2 has more KH value compared to air.
That's okay. CO2 has lower KH value. That means CO2 is highly soluble or more soluble, right, in water compared to argon gas. Okay, so CO2 gas, CO2 dissolves more. Okay, dissolves more in water compared to argon gas. Okay, compared to argon gas. That's the meaning. Okay, so keep this in mind. Lesser the or lower the value of KH, higher is the solubility. Right? Then, so this is what we call as Henry's law. What about temperature? How temperature affects solubility of gas in liquid? Okay, very simple. If we increase temperature, as temperature increases, students, keep this in mind. If we increase temperature, dissolved gas will go out. Correct? If we increase temperature, dissolved gas will go out. So what about the solubility? If more gas is dissolved in water, solubility is high. But if you increase temperature, dissolved gas will go out. That's why if you see in pond, okay, or yeah, especially in ponds. In pond, in the summer season, you can see a lot of fish, okay, will die and it will float. Why? Because in the summer season, temperature will increase. If temperature increases, dissolved oxygen in water, okay, will decrease. Therefore, these aquatic animals, right, they simply die. Okay, so keep this in mind. As temperature increases, okay, solubility of gas in liquid decreases, right, decreases. Similarly, as temperature decreases, suppose if you lower the temperature, yes, you can dissolve more gas, so solubility increases. Very important point, keep this in mind. Okay, yeah, students, I stop here. We'll continue this in the next class, right?